name is Malik Ghallab, and the slides of this presentation are available at this URL, and you have also the URL copied over there. And this tutorial reflects a survey paper that I'm working on with my colleagues here at LAS. So this is a broad overview of integrated task and motion planning. I will not get into and dig into the details of any specific approach to task and motion planning because there are so many of them, but I'll try to give you an idea of what are the approaches and the problems that people are trying to solve in this integration problem. I assume that you are familiar with task planning and to some degree with motion planning, but I'll take time to go into that in a while. So let me first give you my motivation in addressing an integration task. So this is the problem of solving heterogeneous tasks. So basically, I like very much this example of a bird who is interested in some food. At the bottom of this glass, he has a metallical rod, but he's unable to get to the food with that rod. It needs a hook. And he figures out what is needed, and it is trying to make the hook out of its rod. This bird a crow has been raised in captivity, born and raised in captivity. He has not been trained to do that according to the authors, and he never saw some other bird doing this. So it has some planning capabilities to figure out what is needed in order to achieve its goal, basically here to make the specific tool and use it as a hook, and now it is satisfied and it got to its goal. So this is really a very heterogeneous task in terms of all the cognitive and sensory motoric functions that are needed to perform these tasks. So this is a homogeneous task, very intuitively. Playing this game is a homogeneous task. Having an engine for this game is also a homogeneous task. The proof assistance system, very sophisticated for mathematical proof, is also a homogeneous task, and a diagnosis system with Bayesian network is also a homogeneous task. All of these are quite complex, but still homogeneous tasks. Oral translation, in my view, is also a homogeneous task in terms of its representation. This is typically a heterogeneous task, and I believe that this game that you probably have heard of, that was won by the IBM Watson system, Jeopardy, in 2011, is also a heterogeneous task. If we try to define what are homogeneous tasks, basically they are addressable with a unified model and approach, whereas heterogeneous tasks require multiple cognitive functions and multiple computational representations. And then we need to integrate these. So the relationship between homogeneous versus heterogeneous is different from abstract versus embodied task. An abstract task is a task that you can perform in some abstract way without having to carry out actions in a sensory motoric space. But my view is that, however, most embodied tasks are heterogeneous and require several representations. So if AI is about the mechanization of tasks, I would define integrative AI as the mechanization of heterogeneous tasks, including cognitive tasks. So this motivates why it is interesting from a very general viewpoint to tackle integrative problems, and in particular TAMP problems. So this is the outline of this tutorial. I'll introduce TAMP problems, say nothing about task planning or close to nothing. I'll try to present motion and manipulation planning with issues about configuration space, motion planning with PRM and RC techniques, and manipulation planning. Then I'll present representations of how to represent a TAMP problem, task and integrated task and motion planning problem, and several approaches for solving TAMP problems, and then I'll conclude. So this is the outline. It is about 1 hour and a half. I have not planned to take a break, but if you'd like to stop somewhere, we could stop. It's up to you. Maybe we could stop somewhere here. If you feel like taking a break, please feel comfortable to raise your hand, ask questions, and interrupt if you feel like so. I have a quite dense presentation, but we don't need to present everything. So here is an example of a task and motion planning which illustrate my notion of heterogeneous tasks. This is what I call fetch, process, and set generic task, where a robot or an agent in general has to take a collection of objects, to process them somewhere here, and to set them. Setting meaning putting them in the appropriate position, assembling them, it depends on the task, assembling them into some assembly, and it has to do that for a number of objects. So I could consider this task with this simple plan, which says that for each of the objects to fetch, process, and set in their initial position, the robot has to move to a position where the object is reachable. It has to grasp the object. It has to move to the processing position somewhere here. It has to process the object, processing meaning painting it or cleaning it or whatever, depends on the task. It has to move to destination position and set the object in destination pose, meaning again assembly and so on. So this is a very simple plan. We don't even need to generate such a plan. We could script it and just adapt it depending on the task. It's so simple that it's so easy to script it and adapt it by instantiation to the specifics of each instance of these tasks. The problem is that this simple plan does not work most of the time. Grasping means that you are able to grasp, and in many cases, these objects are not graspable as they are giving the constraints of the arm of the robot. They can be graspable in some configuration, but not in other configuration. You have to return them. You have to be in a position where the objects are easily graspable. And the same can be said regarding the processing of the object and the setting of the object. You have to consider not only the simple sequence that I mentioned for each of the objects, but you have to consider the interactions with respect to a number of constraints. You have cluttering constraints that allow not to access an object. You have accessibility and kinematic constraints of the robot. I illustrate that. You may have dynamic constraints. You have assembly constraints depending on how you set the object. And you have other kinds of constraints such as resources, interactions with other agents, and so on. All these constraints make the planning quite difficult, and you have to integrate different representation of your actions, and this needs to be integrated with acting. So you also have to consider the integration of planning and acting. I will not cover this part because of lack of time. It would require really another tutorial just for the integration of task and motion planning with acting. But I'll refer to some approaches that do consider planning together with acting. So these constraints in robotic application range in how important they are depending on the classes of applications, such as domestic robots, service robots, manufacturing robots, industrial robots, industrial mobile robots, and exploration and rescue robots. And the clustering constraints can be very high in domestic applications. They are less important in manufacturing because you will set up the environment such as to avoid a lot of cluttering and so on. So the figures in this table are not precise levels of the constraints of each of the constraints that are here for each class of application. Do not take the figure as something that results from specific studies. They need to be further refined, but you get the idea of some level of constraints that are depending on your class applications have to be taken into account. So you have to do planning with respect to this problem, and you know that planning combines simulation and search. Your simulation step allow you to simulate the possible effect of an action with a predictive model, and your search step searches over a large set of possible organizations of some actions in order to meet the goal or to optimize the criteria. The general picture is that you start from some state and you have a collection of possible actions, for example, action A, and you have a predicted state using your models of A, and you have other actions. And you have to carry on because the next state is not enough until you reach some goal or until you have some collection of actions that optimize some criteria. So this figure, of course, can be made more rich or richer depending on whether your action is deterministic, probabilistic, and so on. So very broad picture about planning, but you have to consider that you have different types of actions that involve different knowledge representations, that have different predictive models, that leads to different planning problems and techniques. And this is particularly the case if you combine motion manipulation planning and task planning. So you have to combine these kind of things. Different types of actions. Motion planning deals with, deal with kinematic trajectories in the configuration space. I'll detail that, and it deals with control and dynamics along these trajectories. Manipulation planning goes into grasping, poses object, forces, and contact, and I'll illustrate that. And you have perception planning that I'm not going to talk about, but at one point, very briefly, communication planning, I said nothing about that, and the general task planning, which we all know about, that consider abstract actions and causal relations, and you generate what is often referred to as skeletal plans, a path in a state transition system at this abstract level for reaching your goal. And the classes of integrated task and motion planning here that I'll be covering are the integration of task and motion manipulation planning. So here is a taxonomy of temp problems. I presented the general fetch, process, and set, but this general fetch, process, and set can be refined into several more specialized problems. For example, navigation among movable objects. In navigation among movable object, I have to move this robot from here to here, but there is this sofa here that needs to, that's on the way, and it needs to be pushed in order to allow the robot to move there. There is the rearrangement of multiple objects, for example, sorting this object, putting the red to the right and the green to the left, for example, for the two objects here. You can have manipulation object, dexterous manipulation, such as changing with the fingers of these hand positions with respect to a particular object. You can have manipulation with non-prehensile actions. You can grasp this object, but not when it is on the table. You have to move it and leave it at the edge of the table in order to be able to grasp it. And you have also structure, assembly, and construction, such as stacking. I'll illustrate an approach for doing this, planning for this kind of things, such as assembly, constructing a bridge, taking into account stability and dynamics. So these are, this is a possible collection of problems that specialize the fetch, process, and set problem that I mentioned here. So each of these is a subcase of the node with inheritance properties between them. So all the examples I mentioned earlier are about the sequential fetch, process, and set, but you could have the concurrent fetch, process, and set, where you have two arms, for example, for doing manipulation or doing assembly. Here is an example of a dual arm manipulation. You can have multi-robot cooperation. You can have human-robot interactions for all of these problems regarding manipulation, rearrangement, and so on. So this is a taxonomy of temp problems to which we will come back later on. And a naive approach to temp is to consider planning only at the abstract level. So we use a task planner and we deal with actions only as state transition systems, precondition effects, and we are done. And we use a motion manipulation planner at the execution level. Once we have a plan, for each of the planned actions, we solve the motion manipulation problems. So this is quite popular. It has been used in the AI robotics community from the beginning. And if there is a failure, you go back to planning and so on. So basically, it requires divisible actions and weakly constraints environment. If all your actions are divisible, that is, you can repeat and so on, because you are backtracking in the real world. It's not a backtracking. In fact, it's a re-execution. Then that's possible. But it can be very inefficient and costly in retrials, because you end up retrying in the real world. And this is not something you would like to do if you'd like to perform your actions efficiently. So this approach is very unsatisfactory in many cases, and the planning really doesn't help much if you do not take into account the constraints that you will see later on, in particular when your environment are a bit constrained with respect to the set of constraints that I mentioned earlier. Consider, for example, this case where the robot has to put these 3 objects on this table here. If it starts with the yellow object, it won't be able to put the 2 others, okay? Because it will not be able to set them in their appropriate position. Consider, for example, the stacking problem, where the robot will not be able to reach the last stacking position because it's too high, given its current location of the base, or given the arm it is using. It has to plan that into account right from the beginning, using the appropriate arm changing position, or taking 2 objects at the same time to stack them at the top. And the other case with dynamic constraints, where, of course, you cannot put the green box before the red one, otherwise the system will be unstable. So let's see how task planning is different from motion planning. Because in all the examples that I mentioned, you need to consider motion and manipulation. The usual way of discussing the difference in the literature is to say that task planning is numeric, that task planning is symbolic, whereas motion planning is numeric. Or similarly, to say that one is discrete, that is task planning, and the other one is continuous. Probably you have seen that before. But this is not the right distinction. In my view, this is wrong. This is wrong and misleading, because you can have everything discretized and still have a significant difference between task planning and motion planning, which is related to metric versus relational. In a metric space, you have a distance. A metric space is structured with a distance, and the distance has to meet these axioms that if your distance is 0, then the 2 states are identical, and your distance is symmetrical and meets the triangular inequalities that you certainly know. And the usual metrics on R to the n are the Manhattan distance for L1, the Euclidean distance for L2, LP, which can be generalized, L infinity, that are used in control. And this distance play a significant role in driving your search and allowing you to plan. And in motion planning, all your spaces are metric. They can be discrete, but they are metric. In task planning, you don't have metric. You have only a relational space, S, which is structured by a set of relations on the lattice 2 to the S. You have only set operations, and you have a relational algebra that allow you to reason about what you add in a state, or how your state changes in there. Your relational space is discrete, but that's not the main point. It is symbolic, but that's not the main point. It is missing a metric. Even if we discretize and keep a metric, this would help a lot. All the work on task planning related to heuristics is because we don't have a metric. Okay? So we need to figure out how far we are with respect to our objectives, and metrics, if your space is structured with a metric, helps a lot. So keep that in mind, because you can have a numeric system without a metric. Do you have in mind an example? A numeric space without a metric. For example, your phone numbers. At some point, we had area codes. Now we don't have area codes anymore. There is no metric because between your phone number and my phone number, the distance can be meaningless, doesn't make sense, and everything is numeric. And again, you can discretize everything and still have or do not have a metric depending on the problem. Motion planning is here, and task planning is here. So another way of handling the integrated task and motion planning is to do hierarchical decoupling. At the planning time, you use task planning to find a sequence of abstract actions without metric parameters, and you use a motion planner to refine each such abstraction into precise metric poses and motion. So this is, in a way, similar to hierarchical planning with downward refinement, which was popular at some point, but has a number of requirements. The downward refinement properties that make this kind of approach feasible are very demanding, and they do not apply here. The assumptions for the downward property refinement do not hold here. The pros is you have a simple integration because you just have to pick up one planner for this one and one another planner for that one, and you organize them hierarchically. But the cons is that this is very complex because most of the computational cost is at this level. I'll come back to that. And because you would lose completeness. Your downward refinement properties do not hold. So this is not a good way of integrating task and motion planning. Instead of hierarchical decoupling, you can try to integrate them. And this integration is needed, again, in cluttered environment, retrial not practical, because of the complexity of motion planning. Backtracking is very expensive, and because your complex actions, if you do any complex actions such as grasping and so on, they do not make sense without metric parameters, because it will change completely your plan depending on where you put the object, what other object you have considered before, in particular with respect to grasping or stability and dynamic constraints. So the state of the art, this is a very active research topic. There are many specialized workshops that have been organized regarding the specifics of the integration of task and motion planning. There is an already large literature. I mentioned that this work stems from a survey that we are working on, and we already have something like 250, 300 papers. I'll comment some of them later on, and you have several techniques that are being explored by this already large literature from a few main perspectives, and I'll try to give you a map of these techniques in order for you to figure out where each stands with respect to these approaches. So the state of the art is already quite rich, but this state of the art is still missing precise comparison and qualification of existing approaches. Unfortunately, I will not be able to give you during this tutorial an idea of this approach works for these problems, and not for that, because we have several, as usual, we have several competing approaches that have been tried for different problems, and we do not have accepted and well-developed benchmarks. And we are lacking a mapping between problems and approaches. What would have been good is, with respect to my taxonomy of problems, to tell you this approach works here, but this approach is better here or there. I'll try to give you some intuition about some of the specifics of that, but I do not have a clear mapping. So don't be disappointed. This is really something missing for the state of the art, and if you are interested in the integration of task and motion planning, I hope you would contribute to defining such a mapping. So which leads me to my next point. As I mentioned, I think that you are all familiar with task planning. Here is a very simplified map of task planning. Most of what I'll be telling in the following will be at the deterministic level. Only one example draws on the probabilistic case. I believe that you know this map, or most of the technique in this map, and I will not present them in any detail. but I refer you to a standard textbook if you are less familiar, but the average attendance of ICAPS knows a lot about that state of the art already. So this is all for task planning. For motion and manipulation planning, I'll say more. Of course, I'll tell you about configuration space, motion planning techniques, and manipulation planning techniques. So let's start with motion planning. So the problem here is to find a path in free space from some initial to a goal position, meeting the robot motion capabilities and avoiding non-obstacles. So I have a description of the robot motion capabilities. This is what we call the kinematics. I have a description of non-obstacles, my initial position, and the goal position. And once I have this path, then at the acting time, I find the control trajectories, that is how to control my kinematics into a dynamic that will allow me to reach my goal. Here also there are a number of classical textbooks. The most recent one is very comprehensive. It is by Steve Laval. Although it's called planning algorithm, it deals with motion planning only, but it is very comprehensive, and I recommend you to refer to this book. The first one by Latombe or the second one by Chauset all have also merits. So are you familiar with the configuration space? All of you? Should I go? No? Should I? Okay, so basically, this is an oversimplified 2 degrees of freedom robot arm. It has just two articulation, angle alpha and angle beta. And this is an obstacle, and this is the configuration of the robot, where alpha and beta have the value drawn here, and this is configuration A, and I would like to go to configuration B. And my possible actions is to change alpha and beta. The actions are changes in my parameter. Here, what I have drawn is the Euclidean space, or the operational space in which the robot operates. But the configuration space is the one that allows me to act, that is changing alpha and beta. If I do any planning, it will be in this space. And the projection of this obstacle in this space is this approximately strange shape. Computing this is very difficult in 2D. And in 3D, it's unfeasible if you have a robot with 50 degrees of freedom, like an articulated humanoid robots. That's not feasible. Here are other examples. Here, you see the projection of my 3 obstacles just for a 2 degrees of freedom arm, the light blue, dark blue, and black with strange shapes. Another obstacle here, and you see that you have, for example, from S to G, the space is connected, but to other configuration, it's not connected because of that obstacles. And similarly for here. So the problem is that this Euclidean space is not what you need for planning. You need this configuration space. So actions are command to modified configuration variables. And your configuration space, denoted C, is simply the Cartesian product of the domain of your configuration variables. And your configuration variables usually are some part of R. For example, in the 2 degrees of freedom robot, the 2 angles are 0, 2 pi, or part of that times 0, 2 pi. And this is the configuration space, and what you are interested in is the free configuration space, the space where there are no obstacles. So computing this free configuration space for kinematic and CAD models is very complex when n is greater than 2, when you have more than 2 degrees of freedom. But testing whether some given configuration is in free space is much easier. This test is very easy. You have very easy procedure that tells you fit or not in the obstacles. So the idea is to trade deterministic completeness for efficiency and to seek probabilistic completeness. So 2 classes of methods: the roadmap method, where you pre-compute a roadmap and you reuse it for answering motion search queries, and diffusion methods, where you solve a specific motion search query by expanding a tree. Let me summarize. Are you familiar with these methods, all of you? Okay, No? So I'll summarize them for those who are not familiar with the two methods quickly. So your roadmap is a randomly generated graph. A vertex is a configuration point in the free configuration space. An edge is a feasible direct motion between two configurations. When I mean direct, that is, you do not have to go around any obstacle. You can just change your configuration directly from one to the next. And you say that the graph covers the configuration space when this property holds. There is a feasible motion in the configuration space if and only if there is a feasible path in the corresponding graph. If this property holds, then you transform motion planning into graph search problems, which is very easy. So here is how it works. I have 2 degrees of freedom, let's say something like a car that could move around, and I have obstacles. And here is the space. I have x and y. This is my configuration space, x and y. And here is what I do. I draw a configuration, and it is in the free space. And this configuration is in free space, covers part of the space. That is, anywhere in this area, I can move to this configuration in a direct line. This configuration is already in an area covered by this one. It does not interest me for the graph per se. This configuration extends my coverage in this new area. This configuration does not. This does not. This extends again. This configuration does not extend. This configuration neither. This one neither. This one has an interesting properties because it is visible from 2 configurations in 2 different areas that are not together. Sorry, this one and that one. So this configuration extends the connectivity of the graph. This configuration does not bring much. Neither this one extends the coverage. This one not. This one allows to connect configuration in different areas, and so on, and this one also extends the connectivity, and at some point you have the coverage property of the entire space, and you know all your space. So this is the way you build the graph. So in a more formal way, the pseudocode is the following. You iterate until some termination condition, you sample a random configuration in your configuration space, and you check whether it is in free space or not. If it is in free space, and if every configuration Q prime already in the graph, the direct path from Q to Q prime is not in the free space, it means that you will extend the coverage because of this configuration Q. Then you add it in the graph. Okay? Here, I have found the configuration that allow me to reach some place not already covered in the graph. If not, if there is a couple of configurations such that Q1 and Q2 are not connected in the graph, and there is a direct connection in free space between the new configuration Q and Q1 and the new configuration Q and Q2, then you add Q and the 2 edges Q and Q1, Q2, and Q1 and QQ1 and QQ2 to the graph, meaning that this configuration extends the connectivity. So here you extend the coverage, here you extend the connectivity, and you keep doing this until some termination condition. So L basically is a kinematic path directly from Q to Q prime in the configuration space. So the termination is related to the number of consecutive and successive samples in the free space that are not added. That is the number of cases where this test succeeds, but neither this one nor this one succeed. You keep finding configurations in the free space, but they do not bring much. And the probability that G covers CF in the precise sense that I defined earlier is estimated by 1 minus 1 over K. So 1K is, let's say, 1,000. You have a coverage of about 10 minus 3 of the entire space. Less than 10 minus 3, that's not covered. And you are happy, and you stop the graph. So basically, you generate a graph, and if you'd like to move, let's say, from this position to that position, you connect your initial and final position to the graph, do your path search, and then smooth out with very simple techniques this path, and at some point you have your path, and you generate a control trajectory along that path. So these are the probabilistic roadmap approaches. And these probabilistic roadmap techniques can be considered with respect to number of sampling strategies. Number of graph connection strategies are presented the simplest, but there are several that are studied in the literature, and available techniques are quite satisfactory in a number of points. So let's move to the diffusion methods, where you do not want to invest into a graph to be used many times, but you are going to do your search only once. This happens, for example, when your environment is very dynamic. So you focus on a randomly generated tree towards the goal. So let's assume that you started from here and your goal is here, and you have already a tree of the configurations over there. You generate a configuration, let's say QRAND, and you try to connect, in this case it is in the obstacles, and you try to connect it to the nearest point in the tree. And then you find configurations between this one and that one, and you extend the tree with this one, and you keep going until you are close to the goal and you reach the goal. So the pseudocode is the following. You have an init tree with the initial configurations. You iterate until a termination with respect to your goal configuration. You sample a random configuration, which is QRAND. You find the best neighbor to the tree, which is QNear, and you expand QNear and QRAND with a new configuration, which is in free space. And this one is added to the tree if it brings something with respect to some distance functions. And you add it together with the edge to the tree. And you keep doing this until termination. And the termination is when you have direct access to the goal. So these are basically the RRT algorithms, and you have a number of variants of RRT algorithms with bidirectional search and so on. So here is an illustration where this humanoid robot is asked to grasp the ball at its feet. So the robot has to step back, because in this position it cannot grasp it. It has to step back and then bend and move its left arm in order to maintain its balance until it is able to reach the goal. So this was done in my lab, you see, to step back in order to leave room for accessing the ball. Everything is done with the PRM technique that I mentioned, and number of degrees of freedom, 34 in these robots, allow the robot to take into account all the kinematic constraints, also stability and dynamics in this case with the left arm. Another illustration of this motion planning capabilities is with humanoid robots. When there are obstacles to the floor, it's not that easy for the robot to move around. Here the task is to reach this position. Giving the obstacles, the motion planning is quite complex, but there is an obstacle that was not there, and the plan has been changed dynamically in order to allow the robot to reach its goal. Sorry. Okay, I'll skip. I had another example in this movie, but I think you got the idea. This is motion planning for closed kinematic loops, where you have a kinematic loop because the two robots are carrying and are linked together kinematically with an object, and this raises a specific number of questions that cannot be addressed directly with the techniques that I just mentioned. So let me move to manipulation planning. In motion planning, we wanted to avoid obstacles altogether. Here, we have to bring a movable object from start to goal positions. And this requires grasping, and grasping means seeking appropriate contact with a movable object. The issue are constrained motions. We are close to the obstacles and the changing environment. We do not try to be away from the obstacles as in motion planning. We have to be close to the obstacles, and we are changing the environment all the time. Here is an example I'll try to illustrate, where the robot has to take this rod that was in this highly constrained configurations. So basically, this manipulation space is decomposed into a placement space and a grasp space. The placement space says where are the possible placement of objects and robots. So as if the objects were free to move, although they are not actuated, and the robot can move freely in the free space. And the grasp space is where the robot can grasp an object regarding to particular possible grasps of the object's poses and the robot. So basically, you consider this placement space. The robot can and the object can be placed in different ways, and the grasp space, how the robot can grasp the object in order to do the manipulation. And the paths in the manipulation space are decomposed into transit passes, where the robot moves along, and transfer passes, where the robot carries movable objects. So basically, these are the main ingredient: the placement and grasping spaces, and the transit passes and the transfer passes. And with that, we'll try to combine the two in order to do the manipulation and solve the tasks that I just mentioned. So you can prove the following properties. A path in a connected component of your placement and grasp space can be transformed into a finite sequence of transit transfer passes. So you can always, if there is a path in this connected component, find such a transit transfer path. So in some abstract projections of your placement and grasp spaces, you have the placement and grasp there. This is their combination, and this is their intersection. And we are going to define a manipulation graph on the basis of this connected component of CP inter CG. So this is the manipulation graph. Configurations in a connected component that can be connected by a manipulation path. So basically, each node here, or each CP under CG area is a node of my manipulation graph, and then I'm going to connect these nodes with arcs that, if they fit in CP, are transit arcs, and if they fit in CG, as you can see here, are transfer edges. So I have my manipulation graph with transit edges, where the robot moves along, and transfer edges, where the robot carries on the objects. And within each of this area, I have the sequence of transfer transit edges in order to perform the grasp and motion. So basically, I end up with a two-level probabilistic roadmap, a roadmap in CP enter CG that you see here in each of these nodes, and a hybrid PRM planner outside of CP enter CG in order to do the connections over the manipulation graph I mentioned. So you define for the CP enter CG your roadmaps, and you define the hybrid planner with transfer passes and transit passes over the outside of CP enter CG. So the hybrid PRM planner can rely on a static roadmap, but because you are changing the environment due to your manipulation, you need to do some dynamic update with RRC in order to avoid obstacles in some particular area, in order to connect the various nodes of your manipulation graph. Sorry if it goes too fast. If you are familiar with manipulation planning, or if you have heard of it, this can remind you of the techniques. Otherwise, this gives you an intuition of how it works. So far, how was it? Understandable? OK, thank you. So basically, to summarize, you have transit passes, a CP enter CG path here, another transit path, a CP enter CG passes here, a transfer path where the object is being transferred, and then a transit path where the robot moves along. And the CP enter CG paths are finite sequences of transit and transfer passes. This works well. Here, an example in a more constrained environment of the same type, where you see how the manipulation is performed and how the planning is performed. So collection of motion planning techniques. Another example where you see the motion of the base and the various grasping and so on. And you have other specific classes such as dexterous manipulations, moving object like this kind of things, tiny sphere or a pen. How to go from this configuration to this one by just moving the fingers, and the constraints has to take into account graph stability. Usually people assume slow motions and no inertial effects, and you can assure the stability by a form of the fingers around the object, like that it is stable here, it is not, or by force closure, but you apply some force and this works here, but it doesn't work here, and the form closure and force closures have different properties, and the minimum number of fingers that are being required depending on the shape here is for any 3D objects. And this is a dual arm manipulation where you manipulate in a highly constrained environment a particular object, a quite complex object. In this case, this was also done by my colleague Simeon from my lab. Doesn't seem very easy task, but the planning is quite elaborate and relies on the techniques that I just presented earlier. Yeah?
What is process on runtime and what is process offline? Like the configuration graph, is this done offline?
Offline.
And the rest is done online?
Online, exactly, yeah. In most of the examples I mentioned, there is no sensing. You assume that you know the environment beforehand. But in some cases, you need to do something, and I'll illustrate some examples. And in that case, your offline computation is very constrained because it relies on what you know beforehand, of course. But here, the manipulation graph is performed offline. So these are the bases for the remaining presentation, where I'll dig into the integration of task planning that I assume you are familiar with the kind of techniques that I just mentioned related to motion and manipulation planning. So let's talk about modeling a temp domain. So in motion planning, we only deal with actions that involve movement. Okay? And actions such as communicating or sensing is not at all representable in motion planning. And we deal with implicit causality. We consider movement, what we do not consider effects per se in the model. They are implicit. If I push, I'm not saying that it will fall or whatever. I just say I push, and the motion follows. For the need of the integrated task and motion planning, we need the preconditions, we need the effects, but we need also something more, which is where to perform the action, and sometimes also how to perform it, because it changes the way you will carry on the motion and manipulation planning together with the task planning. Usually in task planning, we only have that, and in motion planning, we had nothing of this. We just have the kinematics and the model. So a possible classification of action models is to say, in some cases, we have only movement models. All my actions start with movements. Again, there is no remote actions through a switch or communication or sensing that do not involve movement. If you think about your own actions, most of them involve movement in some time, but of communication or sensing that do not involve movement, or thinking, if you consider that as an action that do not involve movement. And you have models that involve movement and causal models. Here, you do not need causal models because all your actions rely only on movement, and here you need causal models. If you have movement models, you need only metric actions only. But if you have movement and causal models, you may have metric actions only as well as generic actions. Metric actions can be described only in metric space, and generic actions have metric as well as logical properties that are non-metric, such as I happen to learn something because of sensing, or to communicate something, or to hear something that are not metric per se. So how do I model a time problem? So basically I need a triple of the environment properties of the world. What are the walls, the fixed obstacles, the shape and the colors of objects and so on, I'm going to work in. I need to define the variable properties of the world, the poses of the objects, and the relationship which object stands where with respect to another object. This is put on top of that and so on. And I need a description of the robot or the robots and all the actuated systems that will act in this environment in terms of kinematics, dynamics, feasible action models, including non-metric actions. So these are the three main components that I need to describe. And I'm going to describe this component with a collection of state variables. So my state variables are a finite set of parameterized state variables, such as, for example, the configuration of an arm, which is a mapping from time or a collection of states, the arm I'm talking about, into R to the 7, which is the set of 7 degrees of freedom of my arm. The pose of an object in space requires 6 degrees of freedom. The fact that an object is on some support, and the supports are a set of tables, shelves, flat surfaces, this is on this support, if I have defined this as support, is simply a mapping between states, time, and the object into the set of possible supports, and so on. So here I have some state variables that are metric and other state variables that are not metric, that I'll call for commodities symbolic state variables. So I'll partition my state variables into those that are range over R and those that range over a discrete domain, the set of support or the set of receptables or some set such as on, off, or a switch. So this set of state variables will be constraints with respect to the environment properties of the world. For example, my degrees of freedom have limited amplitudes of the joints. I cannot move my ankle beyond some angle. I'll have mechanical and kinematic constraints, such as, for example, non-holonomy. Non-holonomy means that your car cannot move sideways. The car cannot move sideways. It is constrained. It has to go back and forth in order to reach a position. Your X and Y are coupled. You have physical constraints such that a solid does not overlap in space with another. It needs to be posed in a material support, otherwise it will fall to the floor. And you can have dependent state variable, which is something we know very much in classical planning. When I say that object 3 is on support 5, this is something that I may be able to compute from the specific pose of in the metric space of object 3, and also the description, geometric description of the support 5 that tells me that this object is necessarily on this support given its pose. So these dependable state variables are computable from other state variables and invariant properties of the world, but they are very useful for your planning. And you can map metric properties into relational ones through this kind of state variables, which will allow you to more easily build your map, and you manage them in some incremental way through planning. So giving my partition of the state variable, I'll partition also the state space into a metric component, which contains all the state variables that range over R, and the non-metric component or symbolic component, which range over a discrete space. So this partition is here regarding Q, what you get in motion planning, and regarding S, what you get in task planning. And task and motion planning is the coupling between the two. So basically, you say that an action is applicable from the state C, which is the couple, given what my definition earlier of Q and S, and brings you to state C prime, Q prime, S prime, through two transition functions, one for the metric components and one for the symbolic components. We are all familiar with this one through the kinematics computation, but what we did in previously is that for the transition from Xi to Xi prime, we had two functions, f and gamma, but previously gamma depended on s and a, but not on q, and q prime depended on q and a, but not on s. And the coupling is due to the fact that each of these transition functions depends on the other state variables. Am I clear? So you have really to consider that in order to move one state to the other one, your metric parameters are in the way, and you need to know them in order to compute the next state. And similarly, in order to compute your next set of metric state variables, you need to know the set of symbolic state variables. And this is the coupling that I mentioned that you need to integrate. And you have to be very careful about not using phi and gamma that decouple entirely. So how do you specify phi and gamma? You specify phi and gamma with local metric methods for computing q prime from q using local kinematics, reachability, and collision detection procedure with motion planning, including constraints due to the symbolic part of the state variable. You have to rely on explicitly asserted change, as in task planning. S prime results by keeping all symbolic variable in S, but of the change explicitly stated in action A, including the parameters, the numeric parameters in Xi, and you rely on functionally defined change. Some state variable in Xi prime are defined as functions of other state variables that are allowed to take into account constraints. For example, X prime is a function of a number of other state variables. And you use what is called procedural attachments, where you have dependent state variables, as in my example of on an object on some support, which summarize several state variables to allow the definition of f prime from this expanded set of symbolic variables. This is really something which is more methodological. There are no, let's say, miracle recipe for defining these functions, but of these general guidelines, and it takes a lot of effort to come up with a good modeling in terms of your representation of a problem. So, solving time problems. Here is the map of approaches in my view and interpretation of the state of the art regarding the integration of task and motion planning. And I try to define the various approaches with respect to how do they organize the search space. So basically, some approaches rely on several roadmaps, and this is the space of roadmaps. Other approaches rely on a hierarchical organization of symbolic metric, and others do something which is mixed. And finally, there are some approaches which rely on combining everything to classical planning. And within space roadmaps, you have different other approaches, and I'll try to give you examples of each of these. So the map is quite rich, several approaches, and I'll try to cover most of them, trying to define how they relate one to the other and what are their differences. So let's start with the space of roadmap approaches. So as I mentioned, the roadmap refers to a unique pair environment robot. Every action but of transfer in free space changes the roadmap. For example, the action touch, grasp, hold, put, push affect both the environment and the robot, and then change the roadmap. So basically, I have a roadmap. I carry some action such as transfer here, and at some position, I change the environment of the robot, and I have to move to some other roadmap. And my search space moves to this other roadmap or to that other one, and so on. So I keep doing collections of roadmaps that I compute while I'm doing my planning. So the space of roadmap is basically that. And it can be defined different ways. Here is one way, which is the planar Asimov that has been defined in my lab. Basically, these are the theses of Cambon and Gravo and a number of other research that we did between 2002 and 2010. So you generate dynamically, and you caches, terrible, and you caches multiple placement and grasp roadmaps, as I mentioned in the manipulation planning. So you have several roadmaps, and you cache some of them because you are going to reuse them, or you hope you will be going to reuse them. And you explore your global space that I just illustrated earlier of several roadmaps that you augment with your symbolic fluence for all the symbolic tasks. And you combine two planners. Initially, we had our motion planners move 3D to build incrementally your roadmaps used to select robots and object configurations and plan movement. You build your roadmaps and you keep them because you may need to go back to them because you have repositioned the world of the robot in configuration where this roadmap is again applicable, or you may have to backtrack. And the second planner is a variant of metric FF. In one of the implementation of Asimov, it was a variant of metric FF to handle symbolic stats referring to the roadmaps of the global space. So the basic actions were go to and switch, go to within a single roadmap, switch motion between roadmaps, grasp, which allow the robot in some position O and in some position P1 and an object in some position P2 to become a new robot in some position P3, which is the union of R and O with respect to this position P3. And this is a robot composition which changes your roadmap because the relationship in the environment and free space and so on have changed. And release where you have robot decomposition. So here is an illustration of Asimov with two robots where the plan requires to move the red box and change a grasp between the two robots in order to plan correctly. So each time there is a grasping or degrasping and so on, you change the roadmap. And you do that taking into account the planning with respect to the abstract actions such as moving and so on, and the concrete actions in this space of roadmaps. Here is a more complex example. This is the IKEA assembly where two robots have to assemble a table from the legs and so on, and the two robots have different capabilities, such as being able to glue things or to fit things in different ways. So there are legs, there is the assembler, there is the sticker, and so on. You have to consider several grasping position. Again, this is what goes with the manipulation planning for the legs, grasping configuration for the table legs. That gives you different roadmaps. You have the grasping configuration for the table board, which illustrates how to do that. CP enter CG roadmap for one robot and one leg. CP enter CG roadmap for two robots and the table, if they carry the table, and so on. And you end up with a collection of something, in this example, 20 or 20-something different roadmaps. This is a transit roadmap for one robot, and roadmap for transfer motions for two robots on the table, and you do your search over there. This is not the entire movie of the plan, because the final result of Asimov is a very redundant plan, a lot of unnecessary action. It's not obviously an optimized planner, but it gives you an idea of the capabilities of this system. So here, the two robots have assembled the two legs. I have skipped a number of things, and they are trying to put the table in the right position. I say that they are trying because they cannot find a direct way of doing so. It appears to be much easier than what they are doing, but it shows that this planning is not that obvious. So they let the table in this position, and then they decide to switch side for some unclear reason, there is no fundamental reason for what they are doing, but only the result of the search that leads to that, and then they are turning around, seeking the appropriate positions in this configuration space. Again, it involves a closed kinematic loops because two robots are carrying the object, and which should be there, and here they are. The assembly is finished. So it is a system with a quite significant set of functionalities. In particular, it allows to take into account two robots, closed kinematic loops, and so on. It has been tested in simulation and in real experiments. It is computationally very demanding, and its scalability is quite limited. This is something that takes minutes of planning time in the order of 20 minutes. And probably it's one of the most complex examples that has been solved with Asimov. Another example of the space of roadmap is the PTR algorithm of Hauser et al. From MIT. I forgot to mention that Asimov is from my lab, or maybe I did. So this is from MIT. Sorry. Hauser is at Stanford. And this is work of Hauser and Latombe. And basically, you are also in a space of roadmap, but a roadmap is associated to each action. So this is a roadmap where action A is feasible, where action B is feasible, and so on. And the transition space is defined such that action B is feasible after A. This is the transition space, which is at the intersection of A and B. In some area of the roadmap where A is feasible, then B becomes feasible. So which leads you to the intuition of how a forward state space search that takes into account fully instantiated state. Fully instantiated state is something very demanding. That is, you know all the metrical parameters of each action to develop an action node with sampling. And in each case, you take k samples, but only one is added to the tree, and you pursue the search. And you do that with some heuristics, where you have sample transitions spaces here, because there are more constraints. Because here, the space is smaller. And you sample there first with this, according to these heuristics, in order to do your search. You have a probabilistic completeness, and this is akin to RRT. This is basically an extension of RRT over a space of roadmaps. This PTR approach has been applied to an hexapod over going on this rough terrain, and also with humanoid robots climbing a ladder. And only in simulation, to my knowledge. Initially, the approach was limited to motion and contact actions only. No general actions, and only metric actions. No causality, explicit causality. Tested in simulation, high computational cost, the scaling up is unclear. The last example I'll mention on the space of roadmap is an extension of RRT, which is called DART, Diverse Action RRT, by Barry and et al. And Barry is from MIT. So basically, the idea is to be able to manipulate with non-prehensible actions, such as moving this plate to the edge in order to grasp it. Using an extended hierarchical search, you find the hierarchy is to find free passes of objects without considering their actuation. You consider objects as if they were able to move by themselves. And these free passes of objects, free meaning freely actuated, no one is pushing them or handling them. You take these as subgoals that are further refined to find appropriate robot actions. It's an interesting approach, again, in the space of roadmap and mostly for numerical actions, but has been able to solve this kind of manipulation and task and motion and manipulation problems with non-prehensible actions. Moving the object until some point and then being able to do the rigid, grasp and then the rigid transfer, and you go on until you put it in the right position. So these are illustrations of the space of roadmap approaches. And let me now illustrate hierarchical symbolic metric approaches. So the idea here is to consider a hierarchy where you have planning at the symbolic transition at some level, and your actions is refined with respect to its metric state variables later on. And you can do this. The arrow here are misleading because they show something like a forward state space search, but you can do this refinement and search in many different ways, and I'll show you some examples in forward and also backward. But the basic idea is to allow this hierarchy between the two levels, which is quite natural. This is the first thing you would think of in doing, coming from the task planning community. So first example is from Garrett and Thomas Lozano Perez and Leslie Pack-Cabling from MIT, the system called FFROB that has been later on extended to HBF, the HBF planner. So you do here a forward search with heuristics with procedural attachments. And again, your states are fully instantiated with the metric parameters. You know the poses, configuration, and grasp of each state, but you require to specify as a user sampling procedures for each classes of actions. So this is a significant requirement because if you do not provide the right sampling procedures, the system may not be as efficient. And you compute with that some interesting set of poses and configurations in order to access or put away objects. And these interesting samples leads you to an interesting data structures called conditional reachability graph that are computed on these interesting sets and allow to map the roadmap connectivity into heuristic functions. So basically, you would like to translate your roadmap connectivity to heuristics as in task planning. And in that case, you use the classical techniques in heuristic forward state space search with this heuristics in order to do your planning. That's why it's called FFROB. You can prove that it is probabilistic complete, and this system has been extended in the other system called HBF, where you combine H for hybrid backward forward. You combine a backward search to provide distance estimates with the forward state space search, which is the basic techniques for doing your search. But these extensions require additional a priori knowledge. You need to define 3 different classes of samplers per actions, and you lose completeness. So this system has been tested in simulation. In an example like this one, this is with FFROB for manipulation, where you have to sort this object, for example, red to the right and green to the left, and so on. 24 objects. And this one for a humanoid robot, where you have to operate a switch here that opens the door access to the green object and take it away and put it close to the blue one. So for example, HBF, which is more efficient than FFROB, plans this for with about 25 actions in 1.5 minutes. So this is FFROB, which is an extension of the usual task planning techniques with the appropriate procedural attachment and ways of computing the heuristics given the roadmap connectivities. My second example is LDC temp, limited depth, combined task and motion planning, by Lagriful from Sweden, Arbro, and his co-authors, again a number of papers between 2013 and 16. Here also you do a state space forward search with backtracking at the symbolic and metric levels with 2 stages, a combined search and a decoupled search. In the combined search, each applicable action at the symbolic stage is metrically evaluated by sampling and motion planning. If your sampling fails, and after a cutoff, because you are only probabilistic complete, if there is a failure, backtracking occurs. If metric backtracking fails, then symbolic backtracking is triggered. So this is the combined. Combined, you do your search over the 2 levels with backtracking at the 2 levels. And the decouple, you ignore the motion planning at the task planning level until you reach a goal. And then you try to instantiate metrically the sequence of actions you found with metric planner. This is something I referred to earlier with this hierarchical decomposition. Here, the idea is you will combine the 2. And in this case, if needed, you perform backtracking at the motion planning level than at the task planning level. And you can find improvement with intelligent backtracking through geometric constraints that I illustrate in a moment. The picture is the following. This is decoupled, where at each point you take into account a refinement both at the symbolic and metric. And if you fail, you backtrack and so on. And you do that until you reach some point in your plan. And at that point, you consider decoupled. And you consider decoupled where you forget about motion planning until you reach a final plan. And then you find through sampling whether this final, let's say, final symbolic plan works at the metric level. And if not, you backtrack and so on. So there is an analysis that has been performed here that show there is an optimal level that allow you to switch from the combined to decoupled, optimal with respect to complexity. And this simplified analysis has been tested in simulation. So basically, there is some level optimal where you start combined and you finish decoupled. Not sure how this simplified analysis holds for large class of problems, but the approach has been applied by Lagriful and his co-authors to things like this set of problems with manipulation with 2 arms moving and inverting the pose of a cup with pick, regrasp, and place actions. We are dealing with plans of about half a dozen to a dozen actions. Another approach is that of the combination of hierarchical task planner with a geometric task planner and reasoner. This is HETP, GTP, that was done also in my lab by over a number of years by 2 PhD students, Garbi and Alami, and my colleagues. So basically, you have an HTN human-aware planner that takes into account what a user of the robot may require, and you model your actions of the robot as well as its human partners in order to foresee what may fit with the demanding human partner. And you do motion manipulation planning such as pick, place, handover, but also perspective taking. Here, the action will allow to show something, to hide something. This object will be reachable by the human, will be observable by the human, and here it will not. So it's a quite rich system with, I have a fast example which shows that the robot is considering in this planning several positions that allow it to reach the object, to put it finally in a position where the end user, which is the green one, will be able to grasp it after interacting with another user. So it relies on partial geometric instantiations and indirect effect of actions. The indirect effect of actions is whether an action is observed, whether in some position an object is observable or not by a user, is reachable or not by a user, and so on. And it is, the search is acted by cost, and the cost takes into account the geometric parameters, and most of the tuning was relied on performing intelligent backtracking. So this intelligent backtracking was the purpose of a set of techniques. All what I mentioned regarding hierarchical metric was with forward search, including with HTN. So I was going to say that this intelligent backtracking triggered a number of research with constraint propagation techniques. In some of them are illustrated in the following approaches. So here you do geometric backtracking with a forward HTL planner, and you perform failure analysis and heuristic ordering of planned actions for intelligent backtracking. And you do that in the case of the extension CSP-ASP by the same group. This is Bidot and Lagrifol from Orbro, to characterize failure with techniques of diagnosis, which is finding possible culprits. This is a parsimonious explanations of what happened in a failure. And you do that with propagation of constraints at two levels: cost geometric constraints regarding position and poses, and bounding boxes regarding possible motions and why motion succeeded or didn't succeed. And this culprit analysis allows you to express inconsistencies as closures as for a SAT solver. That's why they use an ISP solver to do that. And they have been able to apply this system to something as complex as, in this example, to close the lid on this purple box while keeping in it the 6 boxes and the bottle. And this is about 15 to 20 actions in 2 to 3 minutes. The symbolic parts, it takes only 2 seconds here. The ASP solver doesn't cost much. Most of it is in the geometric reasoning and finding why the geometric action worked or didn't work. So a set of complex CSP techniques to analyze possible failures. My final example on hierarchical symbolic metric is the goal regression techniques of hierarchical planning in the no and the belief based hierarchical planning on the no, which is an extension of HPN work developed by Leslie Cabling and Thomas Lozano Perez at MIT. So you do goal regression over a hierarchy of fluents. Your fluents are organized hierarchically by criticality, which is a technique used in task planning, and you rely on specific procedures that the author calls geometric suggestions that gives you metric bindings of parameters. What is desirable as possible metric binding? If I need to pose this object here, what will be a desirable position giving the other constraints? It assumes that your goals are serializable in the usual serializability property of task planning. That is, you can handle them independently, each one of the other, and it interleaves planning and acting. Here is a good example where interleaving is taken into account. So you start with your goal, or one component of your goal, because you assume serializability, and you do goal regression. And your suggester tells you that your goal should be in this particular set of configuration that would be desirable. And you do regression over this possible state with an actions that may allow you to reach this goal. And this is a technique for backchaining called pre-image backchaining that was developed some 20 years ago by Thomas Lozano Perez, of doing the same thing for backchaining that allows you to compute from this configuration that configuration. That's from this set of configuration, this one. And you go on until you reach a position that corresponds to your initial states. And in your initial state, you know your initial configuration, and then you go back until you succeed. Why do you start from the goal? Because your goal is very constrained in terms of configurations. So this is the main argument. This is very constraining, and it gives you something on which you can start working as soon as you get an action that meets your initial configurations. And you do the interleaving of planning and acting because you may not necessarily reach or define your entire plan, given that you have considered just part of your goal, and you assume that your actions are divisible. If something wrong happens, you repeat, or you go back in the real world to previous situations. I'm almost there. Sorry if still have 7 minutes. So HPN has been applied with the caveats, again, that it is not complete, that you start acting without having a complete plan, and you backtrack in the real world. The belief space extensions bring a number of extensions to HPN. One of them, very important, is to handle uncertainty. And you handle uncertainty with Gaussian noise on positions. This is mostly inaccuracy of your positions. Your positions are not known for sure. And you do that with a Bayesian update of state estimates. You do not perform probabilistic search. You have no non-deterministic branching here, but you map these state estimates, Bayesian state estimates, or probability of your positions into a weighting of your cost functions that will be driving your search. You reason on epistemic effects, what the robot knows and does not know in some particular configuration, and if the world changes, the robot may know more, and the robot may move things in order to see other things. This is quite important. Regarding the efficiency, you have factored representations of primitives and entailed fluents. This is the usual factor representations of task planning, and you perform hierarchical search over several levels of fluent criticalities. At the mostly critical fluents, when you are happy with the plan, then you refine for the more critical fluents, but you need to define criticalities. And again, you have interleaved planning and acting. These belief extensions, they call it belief, in my view improperly, has been tested in simulation and with PR2 in problems like the problems you see here, organizing things on a table and putting things on shelves and so on. It is a very comprehensive approach, in particular with respect to handling uncertainty, and it raises a number of significant requirements in a priori knowledge. It seems to be quite robust, but I don't know how scalable it is. So, few things about mixed approaches. Maybe only a few words about the Meta Csp, which is illustrated by the system called CHIMP. A Meta Csp, maybe are you familiar with this notion? So a Meta Csp allows you to make choices to be validated by ground CSP. You always have variables and values and constraints, but your meta variables is a CSP. Your value is an abstract choice over a set of constraints. And when you take a choice at the Meta CSP level, you have to validate it at the ground CSP. So this is implemented in CHIMP, which is a task and motion planner, which combines 4 types of CSPs. 1 for time, 1 for space, 1 for resources, and 1 for causal constraints. So, and you have specific solvers for each one of these CSPs. And the fluent associated to a state variable or to a planned action, its time, space, and resource specification. Each fluent has its mapping into this state variable. In this case, space and geometric constraints are managed by Allen rectangle algebra. It's not a full handling of space and geometry as in the other examples. Allen rectangle algebra is something that extends the Allen algebra for time, if you are familiar with that, to reasoning about the position in 2D. It can be extended to 2.5D between different rectangles, and consider that this rectangle is to the left of that one, or is connected to that one, and to the left and below, and so on. So what you did with the Allen algebra with 2 intervals, you do that with rectangles to consider space. It's quite limited handling of space, actually. and planning stated as a Meta Csp to handle coupling and conflicting effects between different CSPs. Initially, the chimp was using a simple backtrack search algorithm, but they have improved that with an Ishchian approach with methods to guide the search among the CSPs. They have applied that to how to set a table for a waiter robot. So weakly constrained environment, only few objects, about 6 with PR2. I think that the scaling up cannot go much beyond that at this point, in the order of about a dozen objects. Maybe my last example, otherwise I'll be getting into the break, is the approach of Toussaint, which state temp as a minimization problem with respect to a cost functions over the final state. This cost function express your specification of where the object should be set and stability constraints and so on. And this minimization problem is addressed as the first order logic extension of a nonlinear constraint program over trajectories. So this nonlinear constraint program is to find a plan pi and a trajectory x such that you minimize your objective function with respect to x and pi, giving that pi, this plan, entails the domain specifications, and giving that your stability and dynamic constraints are met. So it is, from the mathematical viewpoint, quite elegant approach, and it has been found as well adapted to solve specific classes of problems I'll illustrate in a moment. Let me just mention that the mathematical programming that I stated very briefly is broken into successive approximation stage. You have a first stage which optimizes over all metric parameters in the final state. You have a second stage which optimizes over only intermediate states in pi, giving the results without taking into account trajectories between them, and you have the final stage which optimizes over all trajectories, discretizing in times over 1 and 2. And you do Monte Carlo tree search on your feasible plans. Basically, step 1 is performed for each rollout of your Monte Carlo, and the best plan are optimized with respect to step 2, and if they are feasible with respect to step 3, where you end up finding the motion. And the specific problems in which this approach has been found good are computing and planning this building up of a tower with complex stability properties, simulation with simplified 3 degrees of freedom robot arm, and it scales up with about 50 actions in a minute. Just one word on compiling approach by Vermestre and Hector Geffner, which basically compiles task and motion planning into classical planning using procedural attachment and state constraints. It requires a priori discretization of all your metric state variables, and you do not test collision-free passes in this case. And it has been tested in a limited environment with up to 5 objects into grids of this size, 50 by 50 by 8. It has been improved with a pre-processing stage, but it is, in my view, quite limited as compared to the other approaches. So my conclusion. Metric versus relational space is the basic difference between motion planning, which is metric, and task planning, which is only relational. Both are essential in most heterogeneous tasks. Approaches to TAMP illustrate how to tackle this integration of 2 spaces. The research in TAMP is still facing many challenging issues. Again, I do not have a precise comparison and qualification of all the existing approaches. We do not have a well-accepted and well-developed benchmark for the problems. All this is quite recent, in the order of 15, 20 years for the oldest approaches, and the mapping of problems to approaches, given the taxonomy of problems that I presented earlier, is missing. it will be very good if we can further say that for this class of problems, here is the very good and scalable approaches. I have tried to organize a large collection of available techniques into this map, depending on the search space, which in my view is what characterizes a planning approach mostly. And the main distinctions is between the space of roadmap and the hierarchical symbolic metric. Basically, this is the motion planning a priori approach, and this is the task planning a priori approach, and you have some other approaches such as mixed with Meta Csp and optimization. I believe that most of the work is going on along this hierarchical symbolic metric approach, and I would bet that the most efficient approach will go on along this direction. Keep in mind that task and motion planner is not just the concatenation of a task planner and motion planner, and decoupling doesn't work because of the coupling that I underlined. That metric reasoning for acting is significantly more complex than motion planning in free space because of the contact, because of the grasping, and so on. Motion planning is more computationally expensive than task planning. This is the bottleneck. Motion planning and manipulation planning is the bottleneck. In most figures that are published in the literature, this part takes 1 order of magnitude more time than task planning. 1 order of magnitude more time. And sampling techniques are only probabilistic complete, which means that you have to take into account the cutoff parameters, at what point I'll stop, in order to design your search strategy, because you will have to change these parameters if you do not succeed. And if you do grid-based sampling and grid-based techniques, you're required to manage progressive refinement, taking into account the above points. And finally, deterministic approaches are often insufficient because your positioning are not known, the position of objects are not known precisely, and so on. And your integration of temp has to be addressed together with the integration of planning and acting. And there are possible extensions of the temp integration problems to other problems involving metric and relational space that remain open. In the slides that you can find, there are a number of references to manipulation planning, to motion planning, and references to each of this set of methods that I'm not going to comment for each one. Space of roadmaps, the hierarchical symbolic metric forward, the constraint propagation, and so on. You will see the reference in the slides. I briefly mentioned some of the work during my presentation. So with that, I'm happy to conclude and take your questions if there are any. Sorry if I didn't leave enough time for the discussion. I had too many material to cover, but I'll be happy to take your questions.
So the representation of the joint discrete and continuous space, is it used in any paper, or it's just like you abstract it from many papers?
I abstracted it from many papers.
Okay.
Yeah. No, unfortunately, there is no crisp representation. Most papers have their own representation, and I tried to abstract it for the purpose of this presentation, and also for the survey paper that I'm working on.
Yeah, because I agree with it a lot. But
thank you.
I cannot say in like HTM planning, like this kind of papers.
It works for any approach. It is a general description and modeling. I'm happy that you agree with it, and if you'd like to discuss further, I'm happy to discuss with you. I hope that the survey paper I mentioned will appear soon, but I am not aware of any paper that present the representation in crisp way. Yeah.
And one question about that,
rectangle algebra.
Why is it useful in that paper? I didn't read that paper, but.
Chimp was something that attracted a number of interests because the Meta Csp, you could use a Meta Csp framework without being restricted to the Allen rectangle algebra. It happens that the people working together for designing chimp were knowledgeable about that, and this is something that was developed by one of them. Tony Cohn was the person who developed it. Are you familiar with Tony Cohn? He is a colleague from the United Kingdom who developed these extensions of Allen temporal algebra to space. And they wanted to tackle that because it was, in a way, easy and computationally tractable to handle geometry in that way. But this is certainly a debatable choice. I would not have chosen that, but this is what they did choose.
Thank you. Thanks so much.
Sure. Other questions? Okay. If there are no other questions, let's take a refreshment. I'll be around if you would like to ask questions. I hope that you have been able to get to the slides. Okay. Thank you.